Hello everyone. Welcome to our webinar on building a verified IoT data management platform. I'm Nick Davis, your host for today's webinar. I'd like to welcome our presenters, Ganesh Balamitran and Faizan Montaseri. Ganesh is product manager for the RZIG family of embedded microprocessors at RENESAS Electronics, which are used in IoT gateway and HMI applications. He is responsible for growing the RZIG business in the Americas and bringing to market new solutions for intelligent IoT and embedded AI. Ganesh also brings 20 years of experience in microprocessor product development and marketing to the RENESAS RZIG MPU IoT solutions. Faizan is the founder of ITTIA, a company focused on data management software solutions for embedded systems and intelligent IoT devices. He has worked directly with customers in various vertical markets to define ITTIA's database product roadmap and provide solutions to common data management problems faced by those customers. Under his guidance, ITTIA has grown from its inception to offer a data management solution to prestigious multinational customers throughout North America, Europe, and Asia. Ganesh, Faizan, welcome.
Thank you.
Folks, please be sure to use your Q&A widget to submit your questions. If we don't get through all your questions during the Q&A session, then a reply will be sent via email. Let's get started. Ganesh,
the Internet of Things is changing the way we live. From vehicles and buildings to roads and cities, everything around us is increasingly becoming controlled by devices that come together to automate and improve our lives. Sophisticated computer chips are embedded in objects that each collect and transmit information. The Internet of Things is changing the way we live. The Internet of Things is changing the way we live. From vehicles and buildings to roads and cities, everything around us is increasingly becoming controlled by devices that come together to automate and improve our lives. Sophisticated computer chips are embedded in objects that each collect and transmit information, and these integrated devices interact and analyze a wealth of IoT data originating from sensors, growing into a network of connected objects. When building an embedded system, you need to prepare in-house expertise and be aware of verified solutions. In today's webinar, we will introduce an integration activity from ITTIA IoT Data Factory and show how to benefit from our months of investigation to rapidly build a robust embedded data management solution. We also introduce you to development environment with comprehensive set of tools and plugin features such as SQL database, data distribution service, operating system, and high-performance edge device hardware to accelerate development. Our main goal is to assist customers to accelerate time to market through rapid development with verified tools. All demonstrations, support, and related documents are available at ittia.com/demos. DEMOS. Hello, my name is Faizan Montaseri, and I am the founder and president at ITTIA. I am with Ganesh Balamitran, RZIG product manager at RENESAS. We will share with you the fundamentals that we have learned through decades of interacting with customers to implement an IoT data management platform. I will explain various options for managing data on an IoT edge device, and Ganesh will share characteristics of the right IoT microprocessor and industrial Linux for building these systems. Whether you are measuring temperature, pressure, wind speed, rainfall, or anything else, managing data at rest and in motion is a big challenge. But how do you rapidly select the right tool? Even after you select the right software and hardware, how do you know they will integrate and work together? Today, we have built an Internet of Things demonstration, and we will share the hardware and software tools successfully selected to integrate smoothly to manage IoT data. Our goal with this webinar is to introduce you to our verified data management platform, which was used to build this application. When it comes to building new IoT products, most of the engineering resources assigned to data management are usually spent in configuring and integrating hardware and software components, which can cause long delays. ITTIA IoT Data Factory is a service to recommend the cream of the crop technologies that are verified for IoT data management. By working with data management engineering experts, you will save months of development and integration time. As a result, you will effectively optimize the total cost of ownership and bring products to the market much sooner. A verified IoT platform is the software and hardware components required for devices to collect, share, and take action from the analyzed real-time data. When machines make decisions, those choices should be supported by real-world data and machine learning. Manufacturers building industrial automation, medical devices, power grid, and transportation systems all face a same challenge to harness the incredible power of device data management and connected computing. But this new era introduces a hidden cost and risk. When do you take analysis out of the cloud and put it on the edge network devices? Where do you get a verified hardware and software package to reliably embed data management into your application? Data management comes in two parts: at rest and in motion. Data at rest is stored for analysis by request, while data in motion occurs when devices connect and distribute the analyzed data to other systems and devices. Therefore, to keep up with IoT data management challenges, not only do you require database software on edge devices, you also need the means to connect devices and distribute data. Before we explain the technologies which come together to manage the IoT data demonstration in our lab, let's look at the data management options. Sensors and devices may connect directly to the cloud, where data is centrally managed, or devices may locally collect, store, and analyze the data, and then share the selected findings or information with the cloud. While there is a tremendous emphasis on the promotion of cloud solutions, which promise strong security, devices can deliver the best security by never sharing the complete data at all. Performance, maintenance cost, ownership of the data, and robust connectivity all motivate edge device data management. Now, let's work together and build a real IoT application. In a typical IoT data management scenario, sensors continuously produce a large volume of data for edge gateway devices to consume. These high-performance devices not only need to collect data in real time, but they also need to make the data organized and available. But what are the foundations for managing data and sharing it with other systems? A common IoT data management platform shares, stores, and analyzes data without relying on central storage. In addition, a connectivity solution enables a device to publish information to any number of subscribers over a variety of network configurations. The core operating systems, programming languages, and other development tools provide the foundation for distributed computing. Hardware for IoT devices ranges from low-powered microcontrollers to fully functional embedded computers and microprocessors. In some cases, a dedicated human-machine interface is required to report the status of other IoT devices, provide detailed insight, and offer control. To understand how IoT data management technologies are applied to solve our real-world problems, we are going to look at the electric power grid as a use case. Energy efficiency and cost is a major concern for both residential and commercial buildings. Our demonstration is focused on how to achieve these great savings with electric power microgrid products that leverage our IoT data management framework offering. A microgrid is a local energy grid that can be disconnected from the traditional grid and operate autonomously. A microgrid can be powered by renewable resources like solar panels, energy storage systems, such as batteries or fuel-based generators. This makes it possible for a home business to operate using its own local energy generation, both in times of crisis, such as power outages, and to reduce energy costs. Like other potential applications of IoT technologies, microgrids use a variety of physical devices that collect data and communicate with each other, such as power meters, solar generators, and batteries. When connected to a traditional power grid, it is also useful to share information with the utility company, such as the best times to use battery power. The data management process starts with a device that facilitates communication with the common Internet of Things data management platform and makes all software components work together. To create a microgrid, software must be developed to monitor power load and ensure that energy production meets current demand. Energy storage systems, such as batteries, should be used intelligently to maintain a stable power supply. This requires an awareness of how energy is consumed, both time of day and category. In the same way that an automobile must monitor wear and tear on various parts, or a factory that must monitor production rates. This requires a system that stores and queries data across multiple dimensions. We built a smart home microgrid solution that oversees power consumption through a house. The C++ source code is available at ITTIA.com/demos, DEMOS. Let me also share the hardware and software components that ITTIA IoT Data Factory utilized. This demonstration is built on the RENESAS RZIG microprocessor, ITTIA DB-SQL embedded database, RTI connects DDS, and iWave system on module development board. In our lab, we have this demonstration running to simulate a smart home where sensors are connected throughout the house. Data is directed to a high-performance edge device that is collecting the large quantity of data which will be saved over many months and years. The edge device is also a dashboard that the residents will use to monitor current energy consumption and access reports on energy consumption history. In a future smart home, every object will be intelligent and able to exchange information with other devices. Data is recorded in local database files, including the power produced and consumed by each IoT device deployed throughout the house. These devices communicate with each other to monitor energy usage over days, weeks, months, and even years. Because the data is stored in a database, it is possible to draw a graph for any desired range of time. Each point on the graph represents a record that was found by searching the database. In this scenario, the solar power generator supplies energy during the day and the battery supplies energy at night. A power metering device in the heating and cooling system will show whether the house needs better insulation or other changes to improve energy efficiency. Electric appliances are also monitored to help identify inefficient appliances or indicate when is the best time to use appliances with the high energy cost. Electric vehicles need a great amount of energy over a long time charge, but the vehicle is only plugged in when it is at home overnight. The current status of the system and history is summarized and displayed through the HMI component, which you see now. For this webinar, this demo is deployed on the iWave RZG1 MQ7 system on module development platform, which features USB 3, SATA, and SD slot storage options. Let's look at the embedded software that is running the MICROGRID demo. Using the RTI admin console on our development computer, we can monitor the communication channels that are used to connect the different components of this system. There is a program to simulate the solar generator, another for electronic appliances, one for the electric vehicle, and one for the heating and cooling system. These are all publishing the current kilowatt value using the DDS technology from RTI. Other programs subscribe to these DDS topics to display and record the current state. For example, the current solar reading profile shows how much energy is being produced by the solar power generator. A separate program runs for each sensor, publishing to one of the several DDS topics that are designed specifically for microgrid connectivity. In our lab, these all run on one ARM device, but in practice, they would be deployed to different objects throughout the home. The Data Distribution Service, or DDS, for real-time systems from RTI enables scalable, real-time, high-performance data exchange using the publish-subscribe pattern. To communicate with other components, each meter publishes the current power value as a data object to a DDS topic. Connects DDS handles the low-level messaging and network interfaces. So other components on the same network only need to subscribe to this topic to receive updates whenever the power value changes. This data-centric approach to communications allows each meter to be deployed to a different device without the need to configure a central server or broker to receive the data. But this only gives us the current power values. To accomplish our goal of maximizing energy efficiency in the home, we need to know more about the daily and seasonal power variations of the microgrid. By recording the sensor data to a local database on the IoT Edge network, it will be possible to search through the data with SQL to perform machine learning and subject the sensor readings to analysis. Relational database tables are indexed so they can be filtered and sorted efficiently. ITTIA DB SQL is a high-performance edge device database which is commercially supported by ITTIA for industrial IoT applications. It is tightly integrated into this microgrid application to store a large quantity of data on flash storage media. Using strong built-in data types to clearly organize information. Because the database is fully embedded inside the application programs, there is no need for administration. Deployment is silent. High availability in ITTIA DB SQL also enables the microgrid application to be decentralized, providing secure data management on each device, which can operate with or without connectivity. In this demonstration, the power recorder program runs on each sensor device to save sensor readings in a local database table on flash media. This ensures that historical data is preserved and available even while devices are temporarily disconnected. A new record is added for each sensor measurement at a configurable sample rate using the SQL standard timestamp data type. By sorting a complete history of power measurement in device local databases, the microgrid securely and reliably maintains a complete historical record with high accuracy. The databases are then used to extract a small number of records at specific times for analysis and data sharing. To analyze the data, there are several approaches available. We choose to implement a simple human-machine interface for the microgrid that presents the current power state and history for each sensor. The HMI combines a REST web server, DDS subscriber, and ITTIA DB SQL replication server in a single C++ program. The current power state is cached in memory tables, while sensor history is collected in disk tables from instances of the power recorder program on the devices. The hybrid ITTIA DB SQL database containing these tables is queried whenever a web client requests an update. Concurrent requests are handled safely and efficiently with database transaction isolation, which ensures that every task has a consistent view of the database. Another interesting aspect of the database is having data highly available. Let's look at the replication setting of ITTIA DB SQL. We have the measurement table data, which is configured to replicate data from power recorder, and we have options for changing policies and dealing with the conflicts. All very configurable on fly, and changes can be made inside the database with C and C++ code. We are taking advantage of strong data typing support from RTI DDS and strong data typing of ITTIA DB SQL, and we are using generic mechanism to subscribe and create tables that looks at data types in DDS and maps into data types into ITTIA DB SQL. This is an off-the-shelf solution that developers can benefit from relating DDS data types to ITTIA DB SQL data types. RTI Connects DDS, utilized for this demonstration, is a reliable connectivity framework designed for demanding requirements of the industrial Internet of Things. The MICROGRID HMI is also able to query the full history of sensor measurements collected by the power recorded component, so that the HMI and power recorder can operate independently. Each program keeps its own local copy of the history tables. Database replication is used to send data from the power recorder to the MICROGRID HMI. This ensures that the power recorder is never overwhelmed by a large number of requests, which could impact its ability to record new data. At the same time, the HMI can accumulate data from multiple power recorders, enabling this solution to scale up to support a greater number of power meters. From inception, ITTIA DB SQL was designed for edge device data management. In memory, on disk, and hybrid data management are interesting features of ITTIA DB SQL. We have few tables that store data in memory and few others on disk. Database breach current value from DDS and store them in memory, and recent values are available in the database. There is no need for the data to be persisted, and those tables are in memory. The complexity of IoT integration often surprises integration managers, as costs and development budget rapidly spiral out of control. To prevent disappointment, developer and managers can address the diverse integration requirements for IoT data management by selecting verified tools. There are important factors behind the IoT device data management platform, including interoperability, scalability, security, and standards offered by software technologies selected to build IoT products. For data connectivity, RTI Connects DDS software implements the Object Management Group DDS standard. DDS is an open standard for messaging that supports the unique needs of real-time systems. Its open interfaces and advanced integration capabilities slash costs across systems lifecycle, from initial development and integration through ongoing maintenance and upgrades. The RENESAS RZIG family of ARM-based microprocessors MPUs enable manufacturers to implement high-resolution human-machine interface embedded vision and real-time industrial Ethernet connectivity. It is easy to use design to accelerate time to market, reduces total cost of ownership, and removes many of the obstacles engineers faced when designing IoT and other embedded applications. Software development tools accompanied the RZIG includes operating system, real SQL database, which gets silently embedded in the application, and data distribution software. iWave system on module offers unique advantages in processor scalability and flexibility for data management. Software can work together on compatible iWave hardware to manage sensor data, make decisions, and present information because their development platform comes with touchscreen and rich set of connectors to connect hard drives, sensors, and USB drives.
The platform we have demonstrated today is developed on the RENESAS RZIG family of microprocessors that offer dual and quad-core ARM Cortex-A7 and A15 MPUs with gigahertz class performance. These parts also offer great multimedia with support for multiple streams of decoded H.264 at 1080p 60 and a separate 3D graphics engine for advanced HMI. The RENESAS RZIG family also supports CIP Linux, which offers super long-term support for the Linux kernel, especially targeted at industrial applications that have a long life. RENESAS also delivers a verified Linux package with the RZIG family, and we will go into details in the next couple of slides. CIP, or Civil Infrastructure Platform Linux, is an initiative to develop and maintain an industrial-grade Linux kernel. It was launched as a collaborative project of the Linux Foundation in 2016. The industrial segment requires robust Linux kernels with long-term support as industrial products remain in production much longer than consumer products. With this in mind, the Long-Term Support Initiative, or LTSI, was launched to provide 2 to 3 years of support on every Linux LTSI kernel. The need for automotive-grade support helped launch Automotive-Grade Linux, or AGL. And now in 2016, Linux Foundation launched CIP Linux to provide super long-term support of 10 to 15 years to industrial-grade Linux kernels. RENESAS is a founding member of the Civil Infrastructure Platform and provides CIP Linux support for the RZIG family of microprocessors. RENESAS RZIG CIP Linux is available as a verified Linux package, which enables a quick start to Linux development thanks to a robust out-of-box software framework. The verified Linux platform from RENESAS on RZIG includes GUI, graphics, and multimedia framework, plus a pre-built security package. The verified Linux package is available for download from the RENESAS RZIG marketplace as a pre-built OS image. By starting with this environment, users can avoid a full Yocto build and go directly to application development. The RENESAS RZIG microprocessors, along with the verified Linux package, are included with the RZIG SOMs, or System on Modules, from iWave Systems. iWave offers SOMs for each member of the RENESAS RZIG1 family, and these can be purchased directly from iWave Systems. In this demonstration, we showed how selected technologies work together to solve microgrid problems. But you can see how these could easily be adopted to any IoT scenario where there is data to be managed. The ITTIA microgrid demo solved a specific problem, but the techniques can be applied generally to any application. While the new era of IoT is revolutionizing innovation, ITTIA IoT Factory is a combination of qualified third-party technologies already tested and verified. Consequently, developers save time and rapidly start development. The third-party solution includes RTOS, middleware, connectivity software, user interface, processors, controllers, etc. You have access to ITTIA IoT Data Factory to support this integration and as a first point of contact to answer your questions. Please simply visit ittia.com/demos. An important technical takeaway is that integration of software and hardware solutions, standards, and approaches for the IoT data device journey includes collecting, managing, and analyzing data locally. When there is no connection, devices must still gain insights and make decisions and prepare for data distribution. With the right verified software and hardware technologies, Prototyping IoT devices to manage, share, and distribute data offers tremendous development time, cost, and resource savings. With verified solution, the device data management complexity is reduced. A data management framework is essential. Embedded systems work with data from various origins, and each system needs the right hardware and software to manage and share information. Complex IoT systems consist of many individual products, hardware and software. Although each of them separately work, a total system can behave in unexpected ways. Verified solutions enable us to identify problems early on and validate the performance of the overall system for different layers of technologies needed for successful deployment. This approach offers tremendous savings in the integration and verification of each technology for manufacturing IoT devices.
Okay, thank you, gentlemen, for providing a great overview. And just to review for our viewers, I want to remind them to use the Q&A widget when submitting questions, and that if we don't get through all the questions during the Q&A session, a reply will be sent via email. So now let's dive a little bit deeper with Ganesh and Suzanne and begin our live Q&A session. So the first question is, I saw that you have a password, or I saw you have password protection to access the database. And the question is, how is data protected at rest and in motion? And then they also listed crypto. So if you could answer that, thank you.
Yeah, I can answer that question. This is Ryan Phillips from ITTIA. We have a password protection to protect access to the database for replication or remote access. There's also support for built-in encryption using AES encryption algorithms so that the data stored on the flash media is protected from access outside of the application. And the communication protocols for replication can also be encrypted with TLS encryption mechanisms. The DDS protocol also has support for TLS encryption and certificates to authenticate the access.
Okay, thank you. The next question is mapping data types from DDS to SQL something that I need to write code for, or is it handled with a utility?
Yeah, I can also answer that. So in this demonstration, we are using a source code library in order to enable the mapping that will automatically take data types out of the DDS IDL schema and convert that into database tables and store the data there. We also have integration with the recording service tools from RTI for the DDS service that allows the data from a DDS message to be stored into a database file without developing any source code.
Okay, thank you. The next question is the ITTIA database available for other platforms than ARM?
Yes. The database primarily supports ARM as we are targeting embedded development, but we also have support for Intel platforms and PowerPC platforms as well.
This is a cross-platform solution that is currently presented for this demonstration on Linux, but it's available on other real-time operating systems, and there's no issue with the operating system support for ITTIA DDS2L, as well as RTI DDS.
Okay, very good. The next question is this solution only for microgrid applications? Or pardon me, let me rephrase that. Is this a solution only for microgrid applications? Thank you.
Our demonstration was presented for microgrid. This is a solution that is applicable for very many other markets that they relate to Internet of Things. And we have learned through the years that it can be applied to other markets in addition to what we presented.
Okay, thank you. The next question is, and there's a website listed here that I'll read through it all. Which demo do I need to select on? And the website is ITTIA.com/demos. And then the follow-up question is RENESAS webinar or smart energy, if that makes sense.
The answer is RENESAS webinar. You visit ITTIA.com/demos and you select RENESAS webinar.
Okay, very good, thank you. The next question is this available for AE Cloud 1 or PK S5D9 boards? Did you hear that question? I'm unable to hear a response.
Okay, so system.
We are thinking about that.
Synergy boards.
Could you say that one more time? I didn't hear the answer.
I was telling Ryan and Sasan that the question pertains to the synergy boards.
It's a AE Cloud 1, that is the platform from RENESAS, and I will pass that to you, Ryan, to you, Ganesh, if you can answer that.
We're currently porting the database library to the Synergy platform. This demonstration wasn't built for the Synergy platform, but we can support that with a similar kind of scenario.
Yeah, you basically need to send your request with further questions to info@ITTIA.com, and we will get back to you directly on that.
Okay. The next question is, well, let's go for this one. How can we get the slides after this presentation? Is that something that that we can make available, or that you will make available?
Yeah, that should not be a problem. Simply send a request to info@ITTIA.com, and we can provide you with the slides.
Okay, thank you. The next question, where do I find the CIP image? And then they ask, is it here? And then provide a website. So maybe you all could just provide the website if that's the correct answer.
Yeah, so the website that you have listed, the specific link is to the CIP package, which you can use to build the CIP image for your own board. But if you're looking for a binary CIP image, then it's a different URL. It's on the same marketplace, but it's called the RZIG application development package, because that package is available as a binary image. And I'm trying to see if I can actually answer that, put that URL in the answer here, and submit it.
Okay.
Yeah, so just a moment. See if that actually comes out. It's actually the mp.renesas.com. If you're going to the marketplace, you can find the link to the RZIG application development package. And I'll try and put that into the answer URL here and send it out.
Okay, thank you.
The next question.
Okay, the next question is, how can I configure the database provided by RENESAS according to my project?
Can you repeat the question again, please, Nick?
Yes. How can I configure the database provided by RENESAS according to my project?
Yeah, so the database is configured simply by creating a database schema that's appropriate to the project that you're using. So it's set up in a similar way to working with databases on other platforms, but it's accessed through your C and C++ application code. The database can be initially populated with other development tools as well, though.
Okay, very good, thank you. The next question is there some certification, such as safety IEC 61508, or security certification like EL 2900/IEC 62443 on the RENESAS Linux kernel presented in the demo?
This demonstration is currently verified by RENESAS team, and it's available. And there were a number of certifications that you mentioned, and they're all in the roadmap that we are one-on-one, considering them, and we are planning to support and certify them as we are going to be more engaged with this platform.
Okay, thank you. And it looks like we have just one more question, at least right now, and that is, how is the database replication used in the demonstration?
So this demonstration is using replication to connect several devices together and allow each of them to record its own local copy of the data so that the human-machine interface can run on any of the devices equally, and they'll all have access to the same information that's concurrently produced by the various different devices. For the demonstration purposes, when you download this package, it's set up so that you can run those all on one target board, but if you have multiple target boards, you can run them on separate devices and have them all communicate together.
The demonstration that you download is supported by a complete Getting Started guide that can be valuable, as well as limited support from ITTIA technical support team.
Okay, very good. And it doesn't look like any other questions have come in, so we could hang out here a couple minutes and see if more come in. Or if you guys want to say some concluding remarks, or we could just wrap up the webinar. So it's up to you guys.
Well, I think on behalf of ITTIA, I can thank you everyone for participating in this webinar. And if you have any question that relates to data management and distribution, you can submit that to us via info@itttia.com, and we'll be happy to look at your specific situation and assist you to learn about how data management for the device can assist you to manage, store, analyze a large volume of data and distribute that with other embedded systems as well as devices.
Thanks, Hassan.
Okay,
on behalf of RENESAS and the RZIG team here, I would also like to thank all the participants. The iWave board that was used here in the demonstration is available for purchase directly through iWave, as well as through our distributors like Arrow, Avnet, and Future. So that's a great way to get a hold of the kit to try out the demo. The demonstration is uploaded on the ITTIA website, as was described earlier. And if you have any questions relating to this demonstration or how to get a hold of the kits, you can use the info@ittia.com, info@itttia.com as a first point of contact regarding this webinar and demonstration. Thank you.
Okay. Thank you, everybody. We'll wrap it up. Bye-bye.
Goodbye.
Bye.